When we think of Albert Einstein, we often picture the wild-haired genius who revolutionized our understanding of space and time with his theory of relativity. But there's another, perhaps more intriguing chapter in Einstein's scientific legacy: his profound yet troubled relationship with quantum physics, a field he helped birth but ultimately rejected with his famous declaration that God does not play dice with the universe. This is the story of one of science's greatest ironies. The man who laid the fundamental groundwork for quantum theory became its most eloquent and persistent critic. Einstein's journey with quantum physics began triumphantly in 1905, during his miraculous year, when he explained the photoelectric effect by proposing that light behaves as discrete packets of energy called photons. This revolutionary idea earned him the Nobel Prize in Physics in 1921, not for relativity, as many assume, but for his quantum mechanical explanation of light. But as quantum theory evolved throughout the 1920s, incorporating concepts like wave-particle duality, uncertainty principles, and probabilistic interpretations of reality, Einstein found himself increasingly uncomfortable with the direction physics was taking. The young rebel who had challenged Newton's absolute space and time now found himself in the position of the elder statesman, questioning the new guard of quantum pioneers like Niels Bohr, Werner Heisenberg, and Max Born. What made Einstein's opposition so fascinating wasn't mere stubbornness or inability to adapt. It was rooted in his deep philosophical beliefs about the nature of reality itself. Einstein believed in what physicists call local realism, the idea that objects have definite properties independent of observation, and that nothing can influence something else faster than the speed of light. Quantum mechanics, with its strange phenomena like quantum entanglement and the collapse of wave functions upon measurement, seem to violate these fundamental principles. The debates between Einstein and Bohr became legendary in the physics community, spanning decades and featuring thought experiments that pushed the boundaries of human understanding. Einstein would devise clever scenarios designed to expose what he saw as the incompleteness of quantum theory, while Bohr would respond with equally ingenious counter-arguments defending the quantum worldview. These weren't just academic discussions, they were battles for the soul of physics itself, determining how we understand the very fabric of reality. Today, more than a century after Einstein's first quantum insights and decades after his death, we find ourselves in a remarkable position. Experiments have largely vindicated the quantum mechanical view that Einstein opposed, yet his contributions to the field remain absolutely fundamental. Moreover, his critiques weren't merely obstructionist. They led to deeper insights, including the prediction of quantum entanglement, which Einstein dismissively called spooky action at a distance, but which has become the foundation for emerging technologies like quantum computing and quantum cryptography. This is the paradox we'll explore: how Einstein simultaneously created and rejected quantum physics, and why his failed quest to find a more complete theory continues to inspire physicists today in their search for a unified understanding of the universe. To truly understand Einstein's complex relationship with quantum physics, we must journey back to 1905, his annus mirabilis, or miraculous year, when a 26-year-old patent clerk in Bern, Switzerland, would fundamentally alter the course of modern physics with a series of groundbreaking papers that seemed to emerge from nowhere. Picture this. While his contemporaries in prestigious universities were wrestling with incremental advances in classical physics, Einstein was working in isolation, spending his days evaluating patent applications for electromagnetic devices, and his evenings grappling with the deepest mysteries of the universe. It was in this unlikely setting that he would produce 5 papers that would revolutionize our understanding of reality. and one of them would inadvertently launch the quantum revolution. The problem that captured Einstein's attention was the photoelectric effect, a phenomenon that had been puzzling physicists for years. When light shines on certain metals, it ejects electrons from their surface. Classical physics predicted that brighter light should always produce more energetic electrons, regardless of the light's color. But experiments showed something bizarre. The energy of the ejected electrons depended only on the light's frequency, its color, not its intensity. Dim blue light could eject electrons with more energy than bright red light. It was as if the universe was playing by completely different rules than anyone had imagined. Einstein's solution was nothing short of revolutionary. He proposed that light doesn't behave as the continuous wave that classical physics assumed, but rather as discrete packets of energy, particles of light that he called light quanta, which we now know as photons. Each photon carries a specific amount of energy determined by the light's frequency, following the simple equation E equals h times f, where h is Planck's constant and f is the frequency. This was an extraordinary leap of imagination. Einstein was essentially saying that light has a split personality, sometimes behaving as a wave, as Thomas Young's famous double-slit experiment had demonstrated, and sometimes behaving as particles, as the photoelectric effect demanded. This concept of wave-particle duality would become one of the cornerstones of quantum mechanics, though Einstein himself would later struggle with its implications. What makes Einstein's 1905 photoelectric paper even more remarkable is that he went beyond merely explaining the experimental observations. He made specific, testable predictions about how the energy of ejected electrons should vary with light frequency, predictions that wouldn't be fully confirmed experimentally until Robert Millikan's meticulous work a decade later. Ironically, Millikan initially set out to disprove Einstein's theory, but ended up providing its most convincing verification. But here's where the story takes its first ironic turn. Even as Einstein was laying the foundation for quantum mechanics, he was deeply uncomfortable with the probabilistic implications of his own work. His photon concept suggested that we could never predict exactly when a particular atom would emit or absorb a photon, only the probability of such events. This randomness at the heart of nature troubled Einstein profoundly, even as his brilliant insight was opening the door to an entirely new understanding of the microscopic world. The young Einstein of 1905 had no idea that his elegant solution to the photoelectric effect would eventually lead to a complete overthrow of classical determinism. The comforting notion that if we knew the exact position and momentum of every particle in the universe, we could predict its entire future. He certainly couldn't have foreseen that his light quanta would evolve into a full-blown quantum theory that would challenge the very concepts of objective reality and local causality that he held dear. This pivotal moment in 1905 represents both Einstein's greatest contribution to quantum physics and the beginning of his lifelong ambivalence toward the theory he had helped create. As the years following 1905 unfolded, Einstein watched with a mixture of pride and growing unease as his photon concept began to spawn a scientific revolution that would ultimately spiral far beyond his control or comfort. What had started as an elegant solution to a specific experimental puzzle was evolving into something far more radical and philosophically disturbing than he had ever anticipated. The first signs of Einstein's discomfort emerged as other physicists began building upon his quantum foundation. When Niels Bohr introduced his model of the atom in 1913, incorporating Einstein's quantum ideas to explain why atoms emit light at specific frequencies, Einstein initially welcomed the advance. But Bohr's model relied heavily on quantum jumps, sudden, inexplicable leaps of electrons between energy levels with no classical trajectory connecting them. These instantaneous transitions, with no apparent cause or predictable timing, began to trouble Einstein deeply. The man who had spent his career searching for the underlying order and beauty in natural laws found himself confronting a theory that seemed to suggest the universe operated on cosmic dice throws. Where Einstein sought elegant deterministic equations that revealed the clockwork mechanisms of reality, quantum theory was offering probability clouds and statistical predictions. It was as if he had opened a door expecting to find a magnificent cathedral of physical law, only to discover a casino. Einstein's discomfort crystallized around what became known as the measurement problem. According to the emerging quantum theory, particles existed in multiple states simultaneously, a phenomenon called superposition, until the moment they were observed or measured. Only then would they collapse into a definite state. This suggested that the act of observation itself played a fundamental role in determining physical reality. For Einstein, who believed in an objective reality that existed independently of human observation, this was not just scientifically troubling, but philosophically abhorrent. The situation grew even more disturbing with the development of the uncertainty principle by Werner Heisenberg in 1927. Heisenberg demonstrated that there were fundamental limits to how precisely we could simultaneously know certain pairs of properties, such as a particle's position and momentum. This wasn't merely a limitation of our measuring instruments. It was, according to quantum theory, a fundamental feature of reality itself. The universe, it seemed, was inherently fuzzy at its most basic level. Einstein's response was swift and characteristically incisive. He began developing thought experiments designed to expose what he saw as the logical inconsistencies and incompleteness of quantum mechanics. His famous declaration that God does not play dice with the universe wasn't merely a colorful metaphor. It was a profound statement of his belief that beneath the apparent randomness of quantum phenomena, there must exist hidden variables, unknown mechanisms that would restore determinism and objective reality to physics. What made Einstein's position particularly poignant was that he wasn't simply an outside critic attacking quantum theory from a position of ignorance. He was its founding father, watching his intellectual offspring grow into something he could no longer recognize or embrace. His continued contributions to quantum theory throughout the 1910s and early 1920s, including his work on stimulated emission that would later lead to the invention of lasers, demonstrated his continued mastery of quantum concepts even as he grew increasingly skeptical of their fundamental validity. By the mid-1920s, as quantum mechanics was reaching its mature form through the work of Heisenberg, Schrödinger, Bohr, and others, Einstein found himself in the unprecedented position of being both the theory's most celebrated founder and its most formidable critic. The stage was being set for what would become one of the most famous intellectual battles in the history of science, a battle that would pit Einstein against the very quantum revolution he had initiated and would ultimately define the remainder of his scientific career. The architect of quantum theory was about to become its most persistent and sophisticated opponent.